Um, I wasn't going to do this talk because I've got other projects on the go, but then when I heard there was a speaker backed out, I figured I'll put it together. So this is as a result of probably 2 days worth of work. So anyway, we might moan and groan about politics nowadays, but I think we live in an awesome era. And this is another discovery, I think, like the gravitational waves that are so important. Now, let's see if I can work out how to do that. All right. Before I get to it, I'm going to talk a bit about solar system objects and comets. And this comet is 2P Encke, and it was the second one, of course. The comet itself was discovered by somebody else, but Encke worked out the orbit, and then eventually that's the first person to see it who gets credit. And it looks something like this with the sun, and its perihelion is about a third of the way out. And we actually have Encke's orbit near Toronto called the DDO. And I actually measured the length and width, and it is the shape of the Encke orbit. And I think that was done for a major astronomy conference at the DDO a long time ago, but I'm not sure about that. And if this used to have a sundial, I don't know if it's put back yet. And if that's the sun and this is the Earth's orbit, the closest approach is about 1/3 of the distance. And Karen Mortfield took this because I wasn't feeling well from a copper roof using my camera. Wait a minute, I got to go back a bit. So there are numbers that define an orbit. And the perihelion is one, the peridate, or the date that it reaches, is another, and the eccentricity is another, and that gives a shape, whether it's close to a circle or long and narrow, and I'll get to that later. And there are 3 angles that are involved in the defining an orbit. One of them is the angle between the plane of the ecliptic and the plane of the motion, and the other 2 angles, maybe someone can explain to me, but they're involved. So we have a total of 6 numbers that define any path around the sun. The distance of perihelion, the date and time at perihelion, that's one, of course, the eccentricity, and 3 angles. Years ago, after New Horizons passed through Pluto, I thought, I'm going to try and take a picture of Pluto. So I drove near Luther Lake, northwest of Orangeville, set up my telescope. When it was around midnight, I took a picture of Pluto. And then I went up there 2 days later and took another picture of Pluto. And I'll give you about 20 seconds to see if you can see the dot that has moved from the left photo at the top to the right at the bottom. Can anybody see it? All right. Who's right? And that is Pluto. And when I first looked at the first pictures, I was just overjoyed to see a dot that I thought was the right one. And then I had to go 2 days later. And I wish I'd gone a 3rd day. Because if I'd gone the middle day, this was the 21st and the 23rd, or another day, I would have had enough information to get an idea of the orbit of Pluto. Because there are 6 numbers that define an orbit. And with 3 observations, getting the RA index and knowing the time, I could work out what the orbit is. And every time a moving device or moving object is found in the sky, the powers that be try and get 3 observations, and then they can work out the different coordinates, such as the eccentricity that I'm going to explain in a little bit, or the inclination, that's the tilt, or those other numbers. Okay, eccentricity. And if I'd had more time, I would have got a better diagram than this. If an orbit has an eccentricity of 0, it's a perfect circle. And planets like Earth are close to 0, but not quite. If it's 0.5, it's more elongated. And as it gets closer and closer to 1, it gets longer and narrower as the shape of the orbit. If E equals 1, that's a parabola. And that means an object from way beyond the solar system could have virtually no speed. It approaches the sun, it goes faster and faster, it goes around the sun quickly, and then it goes back out, and it's going to drift away to have virtually no speed compared to us. That's if it's exactly 1. If it's got an eccentricity of greater than 1, That means it's got a positive total energy, so it's going to be quickly moving towards the solar system, whiz around the sun, and then it's going to have enough speed to go out. Now let's go back to this chart here of the different comets. Now this was made about 5 years ago when I gave a talk on comets, and I just used it again. The periodic comets are mostly here, with relatively low eccentricity, relatively close to the plane of the solar system. They actually are from the Kuiper Belt. But there are a whole bunch of comets that are very, very far away from the sun at their furthest approach, almost are escaping into space. If somebody just gave them a kick, probably they would escape from our solar system. And these are clustered around one. But there's the odd comet with an eccentricity greater than 1. And the one that the cursor is pointed to, can you see the cursor there? That's a comet Bowell from 1980. And when they worked backwards to where it came from using the coordinates, it turns out it had a close pass near Jupiter, and Jupiter sped it up, and it whizzed close to the sun, it came back out, and it's moving away from the solar system. That was the most high eccentricity comet until, okay, sorry, I haven't practiced this enough, so I'll go back. I was talking about going past Jupiter. If an object goes past a planet and the planet can accelerate it or it can decelerate it, so often when something goes past a planet, it can get accelerated to enough to leave the space. Anyway, then came this discovery of, and I have no idea how to say it, Oumuamua? Oumuamua? And I'm going to discuss, all right. It was discovered first in a telescope in the Pan-STARRS telescope. And they picked a Hawaiian name. I think they talked to some experts in Hawaiian language, and they picked the Hawaiian name. And it literally means a messenger from afar arriving first, except it also means scout. And a lot of people wanted to name it Rama after the Arthur C. Clarke story where an object comes from elsewhere and it turns out it's a rocket and people explore it and everything. I haven't read it. Has anybody read that one, by the way? Any of the Rama? Okay, am I mostly right? Okay. All right, I just want to explain the notation. Comets were something like 2P, which means the second periodic comet, and this is the first, and the I stands for interstellar, of course that's the year, and the U stands for the particular month, which is the second half of October. Here's the discovery image. I missed Ralph's talk on vision and aging, because there must be something wrong with my eyes, because I never see red lines like this in the sky when I look through my telescope. I don't know. This is the discovery image. It doesn't look like much, but it was enough. And they noticed right away that it moved really quickly, and that led to further discoveries. Incidentally, the team from Karen Meach's paper, I've looked at 2 papers on this, includes Robert Warwick, who is from London, and he's going to be speaking at the London Center this Friday. So if anybody wants to know more about it and perhaps correct information from him, just drive down to London Center. You know, they have a website, and you can find out when. I doubt if I'll go, but I might. And Robert Jedicke, who also is related to Peter Jedicke, and I don't know if they're Canadian or whatever, but anyway, there is a Canadian connection to this. Where did it come from? Well, it's hard to make a 3-dimensional diagram, but it basically came from above the solar system near Vega, which will be our pole star in, I don't know, 10,000 years or so. So this is July, August, September 9th, it was closest to the sun, or perihelion. Then it made a sharp turn around the sun. October, and it was October 19th that the image that I showed you was taken. Can you imagine the panic of experts on this to say, wow, we got to study this. putting the proposals together to get directors, discretionary time at telescopes, and putting everything together. It must have been a mad rush, and I'm sure some people went through a few weeks without any sleep. The observation that I'm going to talk about were taken about here, and right now it's somewhere around Jupiter. Yeah, it's somewhere around Jupiter. Okay, its speed compared to the sun, it was 87 kilometers a second at perihelion, and in interstellar space it's 26. And my calculations is it's about 11,500 years to travel a light year. Now, it comes from the area of Vega that, of course, is fairly high up. And I estimate it would take about 2,800 years to get to where Vega is now. But everything in our galaxy is moving. And it turns out that the Ring Nebula, this is the center of the galaxy, of course, and we're here. The Ring Nebula is fairly close to Vega, so we're looking a little bit, not across the galaxy, but a little bit into it. And Vega wasn't there when it started, so it did not come from Vega, so Jodie Foster doesn't have to worry about finding her father or whatever. It came. I actually heard that some people think it might have came from Carina. And it's almost as if this part of the galaxy is moving at a different speed than this. I don't know. And needless to say, this is being worked on. So is it a comet or an asteroid? This thing's moving so fast. Oh, yes, I know what I was going to say. Near Vega, there's no evidence of any distant planet there. And, you know, they've talked about finding Planet 9 that might be out there. Well, it's not in that part of the sky. So they're pretty sure that it's not being deflected by something big out there, but it came from somewhere else. So this is a photo from before processing. Then they processed it, and they worked out how the brightness declines with distance. So this is the angular radius in the center. So this is 1 arc second. This is 10. This is the maximum, so this is 10%, like logarithm of 1, so that's 10%, and this is 1%. See how it drops really quickly? And actually, a star would drop about like that. But wouldn't you expect a comet to have a little bit of dust coming off and a layer? So for some reason, this object not only is from going faster than anything else, but it doesn't produce any dust. But this object has gone close to the sun, inside Mercury's orbit, and gone out. It's been close to the sun for a fair amount of time, so why not? This is a picture that Philae took of the comet Churyumov-Gerasimenko 69P for the few days before it ended up dying. And this surface, or at least parts of it, have volatiles that when the sun hits it, they send off dust that end up making the comet tail. But this doesn't. So why? One explanation. Cosmic rays over the million years or whatever it was in space removed the volatiles down to about a half a meter because the heat from the sun only could have gone that deep. So that's one theory. Another is this is an asteroid with few volatiles. And in our solar system, somewhere a little inside Ceres, we have the difference between the snow line and the inner planets. It's so hot that any water that gets in a planet is going to be sublimate away unless it's cold enough, unless there's enough gravity to hold it like we do. So this thing probably came from here, or maybe it came because it was knocked out of a planet. But how would you get a shape like that knocked out of a planet? I don't know. Maybe, Chris, you know something about the geology of it, but I'll get to that in a minute. I see you shaking your head. Then they took a spectrum, and they look at the different colors, and this object that was called A, but now is called 1I, has this spectrum with quite a wide range, but it looks like a C-type asteroid that would be carbonaceous chondrites, or an S-type asteroid that is a stony, has a different pattern, so it's not like those two, but it's similar to D-type asteroids and some comets, but this is shaky data. And it turns out that some of the Trojan asteroids, either behind Jupiter's orbit or in front, are similar when they take the spectra. But again, it's shaky data, and they're not quite sure. Now I get to the light curve, which is really strange. There's so many strange things about this object. There's one team led by Karen Meach, including those two Canadians, and I've coded them in red, and they were able to get observing time on the Canada-France-Hawaii telescope. There's a UK infrared telescope and Keck in Hawaii, and the very large telescope in Gemini South in Chile. I don't know which one is north and which is south. I don't know. Any Chilean experts here? Okay, anyway. The other team in blue by David Jewett and a few others who found the first Kuiper Belt object other than Pluto, they got time on the Norwegian optical telescope? No, Nordic optical telescope in the Canary Islands and a couple of telescopes in Arizona. What have I done? So here's some light curves. This thing gets amazingly bright and faint as it tumbles. So this is the magnitude. So as you go down here, it gets fainter. So this is magnitude 25. And notice that the error bars are much larger for the faint observations than for the bright ones. I guess this was daytime, so they didn't see it. Then the next day on October 26th, this is what, 6 days after the discovery, 7? This was 6 days after the discovery. That's pretty fast to get telescope time, director discretionary time. So here they have good data where it's, and then wobbly data there. The Meach light curves and this as well. Then the other group, what they did is they arranged it so it was all in the same cycle. So you have this from one day, this from another, and they're able to analyze. So what causes the varying brightness of these things? Well, it could be there's a bright spot-like series on it, or I think it's Iaptis, the moon, that has a dark hemisphere. That's one of the facts I wanted to check before I did it, but I ran out of time. So here's the summary from Karen Meach's group and David Jewett's group. They get close periods, and 8 hours is a typical time for asteroids to get bright and faint. The brightness range from this group is 2.5 magnitudes, which is 10 times factor. This group is only 2 magnitudes, which is 6.3. If it were a cylinder, and I forgot to bring it in, I'll use this. If it's a cylinder, this would be the faint part, this would be the bright part, faint, bright. Do I mess up the, okay. Now, I don't know why, but they used a different assumption of albedo, which kind of messes up the calculation because these guys predicted this dimension and these people predicted a different dimension. But when you can only see the light, the brightness of an object, you have to assume a certain brightness to estimate how big it is. So the answer to how big it is nobody really knows. But this is the two science papers. Okay, for comparison, Comet 67P is 4 kilometers long and about a 12-hour rotation. Now, notice that it's sort of like a duck, and actually they've proven that it's made out of 2 asteroids that gently nudge together over the eons in the outer area, and then slowly, I don't quite know what process, but they're together. But if this thing spun too quickly, I think the 2 bits would fly apart because there's nothing really holding them together. Now, if you have this object, Oumuamua, 200 meters long and an 8-hour rotation, that is so fast this would have to have strength to hold it together. Now, I was talking to a friend, or emailing a friend about this, and he talked about, was it Devil's Mountain, Scott, that you saw in, where was that? Wyoming? And he was wondering if there happened to be a structure like that on another planet and maybe something hit it and knocked that into space. I don't know. I don't know what would cause an object to form this way with enough tensile strength to be able to rotate. But there's always the option that it's not natural. It's a rocket. And we blew it. We didn't chase after it to say hi, but, you know, whatever. But I heard, I read just a day ago that the Green Bank Radio Telescope is going to observe it for 10 hours, starting at 3 o'clock in the afternoon. And I checked just before the meeting on my cell phone if there was any announcement that they had found ET, but nothing got on the news. Maybe there's too much about Trump to fit that in. This is an article in the February 1997 Astronomy by David Stern, who was the principal investigator for the New Horizons mission. And he talks about all sorts of reasons that there are millions or billions or trillions of these objects, including several right now between us and the sun. But we have trouble detecting them. But there are clearly a lot of objects from elsewhere that are coming towards us, and we're just finding out about them. And just as gravitational waves started with one, and then you get more and more and learn more and more, I predict this discovery with better observing techniques are going to find more and more visitors from other planets, and boy, we live in an exciting time. Thank you very much.
Any questions for Rob?
Yes.
James Webb will make a difference when that goes up? The James Webb Telescope, when that goes up, do you think that's going to make a difference in observation?
Is it working?
Yeah.
Okay. The James Webb Telescope, I don't know if it's that good a telescope for wide-angle views. And to do searches for objects like this, you need a telescope that can see a wide-angle patch of sky, and you do continual surveys all around. But when they find an object, the James Webb would be perfect to focus on it to get information. And I'm impressed with the telescopes they were able to get online, but I'm astounded that they didn't throw everything we have at that object. You know, Hubble, all the Kecks, there's a monster telescope in the Canary Islands that I think is the biggest in the world. Why wasn't everything thrown at it to get the best possible observations? And it looks, at least on the basis of the two papers I saw, only a few telescopes where they got director's time to do it. But if James Webb, or once James Webb comes in and they find another, it will provide good data about these as well. And the advantage is it can watch it continually if they can get the time, because you know, you can only watch for sort of 12 hours and then it sets, and you've got to count on other telescopes to make the difference. So to have a space telescope observing it, I think, would be wonderful. Did I answer your question? Yep. Okay. Yes.
Hi, first of all, thanks for that very fascinating presentation.
Thank you.
And when you were talking about the orbits of these asteroids and comets, the eccentricities, so say when the eccentricity is greater or equal to 1, say you have a parabolic or hyperbolic orbit, does this mean that the orbit is unbounded? Say you have a comet that moves in, approaches the perihelion, moves past, exits the solar system, and never once again enters the solar system.
Exactly.
Really?
Yes. And
fascinating.
There's, I showed the last article by Alan Stern, and he says there's so much evidence in terms of theories of how the solar system formed. The definition of a planet is it clears its orbit, and we clear our orbit by some object going close to us, and we deflect it, and it goes out.
Oh, really?
So anything with a hyperbolic orbit, eccentricity greater than 1, is going to leave the solar system unless it happens to go near a heavy object, and then it's going to get bent back in again.
I see.
Sorry, Paul.
So the limit or the upper threshold for the eccentricity of a bounded orbit is 1.
Of a what?
Of a bounded orbit, say
Yes.
a circle or an ellipse. I see. Okay, wow.
I just want to make a little caveat here.
Okay.
The eccentricities change as the objects move out. Because when it's close to the sun, the mass that is attracting it is the sun's mass. But as it goes further out, we're talking about something that's 1.002. Okay? As it gets further out, now it's attracted by the whole mass in the solar system, Jupiter, Saturn, etc. And it actually, that extra mass slowly can decrease the eccentricity, so it might come back again if it's, say, 1.002 or, I mean, I don't know the exact, but there is a small factor like that. Okay?
So this sounds like it would possibly go into, say, non-Euclidean geometry because of the masses of all of these bodies.
Yeah, it's interesting.
Wow.
Yeah.
Interesting. All right. Thank you.
I then have one more thing to say. Merry Christmas, everybody.